Imagine a black silhouette rolling across a moonlit desert runway so dark it seems to drink the light, and imagine that it is leaking fuel onto the concrete as it goes because it was never truly built for the ground at all. This aircraft was designed to be uncomfortable at rest and perfectly at home 80,000 feet above the world, where the sky turns to velvet and the horizon quietly begins to curve. It was built to grow, to stretch, to seal itself shut only once the friction of the air had heated its skin to a glow. And here is the strange part, the part that still feels impossible. When enemies fired missiles at it, the standard response was not to dodge, not to hide, but simply to accelerate away. Tonight, let your breathing slow while we follow this machine from the whispered paranoia of Cold War hangars, through the titanium and firelight that shaped its body, to the pilots in pressure suits who crossed continents faster than sound and described the experience as oddly, beautifully calm. This is the story of how a small group of engineers solved a problem no one believed could be solved, and why, decades after its final quiet landing, nothing has ever flown fast enough to take its place. There is a moment, somewhere in the high desert of California, just after midnight, when the runway lights stretch out in two long parallel lines and the air has finally cooled enough to feel soft against the skin. The sagebrush is still. The tower is quiet. And then something moves at the far end of the concrete, something you notice more as an absence than a presence, a long black shape that seems to swallow the moonlight rather than reflect it. It does not gleam like an airliner. It does not flash like a fighter. It simply sits there, low and impossibly stretched, with a nose like a needle and wings that seem to melt into the fuselage, as if the whole machine had been poured rather than built. And if you were standing close enough on a night like that, you would notice something strange. The airplane would be leaking, small dark beads of fuel gathering beneath it, dripping onto the pavement in slow, patient rhythm, forming a little pool that the ground crews had long ago stopped worrying about, because they knew that within minutes of flight the metal would swell tight and seal itself, and the leaking would stop entirely. That single detail tells you almost everything you need to know about the SR-71 Blackbird. It was an aircraft so specialized, so tuned to one narrow band of extreme conditions, that on the ground it behaved almost like a broken thing. It was uncomfortable at rest. It was only truly itself at 80,000 feet, moving faster than a rifle bullet, with its skin glowing hot and its body stretched several inches longer than it had been at the gate. Everything about it was designed for that one place in the sky, the thin, cold edge of the atmosphere where the horizon curves and the air is too sparse to hold you up unless you are moving with tremendous speed. And here is the paradox that sits at the very heart of this story, the one that has kept engineers and pilots and dreamers coming back to this airplane for more than half a century. The Blackbird was built during the most dangerous decades of the 20th century, at a time when surface-to-air missiles were becoming faster, smarter, and more numerous every year. The standard answer to that threat was armor, or countermeasures, or stealth. But the people who created this aircraft chose a different answer entirely. They decided that the safest place to be was simply out in front, not hidden, not protected, just faster. So they built an airplane whose primary defense was acceleration, a reconnaissance aircraft whose emergency procedure when a missile was launched at it was often nothing more complicated than to push the throttles forward and climb. And it worked. Over roughly 24 years of operational flying in some of the most heavily defended airspace on the planet, not a single SR-71 was ever lost to enemy fire. Missiles were fired at it, by some accounts, many hundreds of them, and every one of them arrived where the Blackbird used to be. Think about that for a moment, slowly, the way you would turn a smooth stone over in your hand. Human beings built a machine that could outrun the weapons designed specifically to destroy it, and they did it with slide rules and drafting tables, with hand-shaped metal and grease pencil calculations in an era before the pocket calculator existed. There were no computer simulations to warn them about what would go wrong. They had to imagine it, guess it, test it, and then live with the answers. So this is not really a story about a weapon. The Blackbird never carried a bomb. It never fired a shot. It carried cameras and sensors and film, and its entire purpose was to look, to gather, and to come home. Which means that in a very real way, this is a story about curiosity, about the almost unreasonable lengths that people will go to in order to see something clearly. It is a story about patience too, because nothing about this aircraft came quickly. Every solution created a new problem, and every new problem required a material or a technique or a fuel that did not yet exist and had to be invented from scratch. Ordinary aluminum would have softened and failed in the heat of Mach 3 flight, so they turned to titanium, a metal that was difficult, expensive, and stubborn to machine. Ordinary jet fuel would have boiled and vaporized, so they created a new one with a higher flash point, so stable that you could reportedly drop a lit match into it and watch the flame go out. Ordinary windows would have cracked. Ordinary tires would have exploded. Ordinary paint would have burned away. So they changed all of it, one patient step at a time. That is the theme I would like to leave with you tonight, and it is one we will return to again and again as this story unfolds. Call it the lullaby of engineering. It is the quiet, repetitive, deeply human rhythm of noticing a problem, sitting with it, and solving it a little at a time, not with drama, not with lightning bolts of genius, although there were flashes of those too, mostly with attention, with hundreds of ordinary people showing up day after day in a windowless building, working on something they could not tell their families about, chipping away at the impossible until it became routine. There is something enormously calming in that idea. The world is loud and the world is fast, but progress, real progress, tends to move at the speed of steady hands. Over the hours ahead, we are going to travel that whole arc together, gently, with no rush at all. We will begin in the shadows of Cold War secrecy, in a time when high-altitude reconnaissance flights were the only reliable way to know what the other side was actually building. We will visit a group of engineers working inside a deliberately unremarkable facility in Burbank, California, a place nicknamed the Skunk Works, where a lanky, gruff aeronautical designer named Clarence Johnson, known to nearly everyone as Kelly, believed that a small team of talented people with very little bureaucracy could accomplish things that enormous organizations could not. We will follow the strange, secretive first cousin of the Blackbird, an aircraft called the A-12, as it lifts off from a dry lakebed in the Nevada desert in the spring of 1962, watched by almost no one, its existence denied for decades. From there we will move into the metal itself, into the puzzle of titanium and the peculiar problem of building an airplane out of a material that expands when it gets hot and shrinks when it cools, which meant that the finished aircraft had to be designed loose, with deliberate gaps and corrugated skin panels, so that it could grow into its proper shape only once it was flying. We will talk about the engines, which were less like ordinary jet engines and more like clever hybrids that changed their own personality as the aircraft accelerated, quietly transforming from turbojets into something closer to ramjets, with spike-shaped cones sliding forward and backward in the intakes to tame the shock waves and keep the airflow exactly where it needed to be. We will talk about the crews too, because none of this happened by itself. 2 people in each aircraft, sealed inside full pressure suits that looked very much like the ones worn by astronauts, breathing pure oxygen, eating through a tube, watching the sky above them turn from blue to indigo to something close to black. We will talk about what they saw up there and what they felt, and how a pilot describes the sensation of looking down at the curve of the Earth from more than 15 miles up while the windshield beside his face grows too hot to touch. And eventually we will come to the records, the ones still standing today. A dash across the Atlantic from New York to London in under 2 hours, a sustained altitude, and a level flight speed set on a July afternoon in 1976 that no air-breathing aircraft has ever officially surpassed. Numbers that have simply sat there patient and unbeaten for decades. But all of that can wait. For now, stay with that first image, the desert night. The 2 lines of runway lights running off toward the mountains. The long black shape at the end of the pavement, dripping quietly onto the concrete, waiting for the cold air and the clearance and the moment when everything that seems wrong about it on the ground becomes exactly right in the sky. Breathe slowly. There is no hurry here. We have all night, and the story only gets stranger and more beautiful from here. In the middle of the 1950s, the United States and the Soviet Union were 2 enormous countries staring at each other across a wall of almost total ignorance. That is the strange thing people forget about the early Cold War. It was not simply that the 2 sides distrusted one another, it was that neither could see the other. The Soviet Union was a closed landmass covering 1/6 of the planet's land surface, and behind its borders there were factories, airfields, missile test ranges, and construction sites that Western intelligence could only guess at. And guessing, when the subject is thermonuclear weapons, is a very uncomfortable thing to do. You can feel the anxiety in the phrases that entered the language during those years. The bomber gap, the missile gap, both were born from the same problem, which was a shortage of facts. In the summer of 1955, at an aviation display near Moscow, Western observers watched formations of Soviet Myasishchev bombers pass overhead and dutifully counted them, and the numbers they wrote down suggested an enormous fleet. Later analysis suggested something far less dramatic, that a small number of aircraft had simply flown in a wide circle and come around again. Whether that was deliberate theater or a coincidence of scheduling hardly mattered. What mattered was that an entire national estimate could swing on a handful of men squinting at the sky with notebooks. That was the state of the art. That was how much the world's most powerful nations actually knew about each other. So the pressure to see became enormous. Not curiosity, not competitive pride, survival in the plainest sense. If you believe your rival has 400 bombers when he has 40, you build weapons you do not need, and you frighten him into building more of his own, and the spiral goes on turning. Photographs, real photographs taken from directly above, were the only way to stop the spiral. And in those years before reliable satellites, the only way to get directly above something was to fly there. Which brings us to a plain building in Burbank, California, sitting beside a busy airport, with no sign out front announcing what happened inside. Lockheed's Advanced Development Projects Division had earned its nickname during the Second World War, when a small team crammed into a rented circus tent next to a plastics factory that gave off a truly memorable smell. Somebody made a joke about the moonshine still in a popular comic strip of the day, The Skunk Works, and the name stuck, softened slightly into Skunk Works. In 1943, that team had designed and delivered America's first operational jet fighter in 143 days, and the lesson Kelly Johnson drew from that experience shaped everything that followed. His idea was almost embarrassingly simple. Keep the team small. Keep the paperwork thin. Put the engineers within a short walk of the machinists building their drawings so that a question can be answered in 90 seconds instead of 9 weeks. Give one person the authority to decide and let that person live with the consequences. Johnson eventually wrote his principles down as a short list of rules, and the spirit running through all of them was the same, which was that the enemy of a difficult project is not difficulty. The enemy is delay and committees and the slow accumulation of people who can say no but cannot say yes. Secrecy, oddly enough, helped. When a program is classified deeply enough, it disappears from the ordinary machinery of oversight and review. There are no press briefings, no congressional demonstrations, no long afternoons explaining a design choice to someone who will never build anything. There is only the work and a very small circle of people cleared to know it exists. That isolation could be a burden, and it certainly was for the families who never learned what their fathers actually did all day. But for the engineering itself, it was a kind of greenhouse. Impossible ideas could be tried and could fail and could be quietly tried again, without anyone outside ever hearing about it. The first great product of that greenhouse was the U-2. Johnson's answer to the reconnaissance problem was, in essence, a jet-powered glider. Enormous wings, a body stripped of everything that could be stripped, an engine, a camera, and a pilot. It first flew in the summer of 1955, and it could cruise above 70,000 feet, which at the time placed it comfortably beyond the reach of Soviet fighters and beyond the ceiling of their surface-to-air missiles. The photographs it brought back were extraordinary. For the first time, analysts could look at an airfield in Central Asia and count what was actually parked there. But there was a flaw in the plan, and it revealed itself almost immediately. On the very first overflights of Soviet territory, in the summer of 1956, the U-2 was tracked on Soviet radar. It could not be intercepted, but it could be seen, and being seen meant being expected. Every flight after that was a race between American altitude and Soviet air defense development, and altitude is a fixed quantity while development is not. Lockheed tried to buy time with a program to reduce the aircraft's radar signature, hanging wires along the fuselage and coating the airframe in absorbing material. The modified aircraft were nicknamed Dirty Birds, and they flew heavier, hotter, and lower, which rather defeated the purpose. The fix did not hold. On the 1st of May 1960, a U-2 flown by Francis Gary Powers was brought down near Sverdlovsk by a salvo of SA-2 missiles. Powers survived, the wreckage survived, and the entire American position, which had rested on the polite fiction that these were weather research flights, collapsed in public over the following week. A summit conference in Paris fell apart. Overflights of the Soviet Union by manned aircraft ended, and they never resumed. The U-2 had been a magnificent answer to the question, and the question had simply changed underneath it. Here is the thing, though. That vulnerability had been anticipated. Years before Powers went down, the men running the reconnaissance program had understood that altitude alone would eventually stop being a shield, and they had begun asking for something else. Under the codename Gusto, and then under the name that would carry it to completion, Okhkart, the Central Intelligence Agency went looking for a successor, and the requirements they wrote down read less like a specification and more like a wish. They wanted an aircraft that cruised at better than 3 times the speed of sound, not a dash, not a brief burst, but a sustained cruise, hour after hour. They wanted it to fly above 90,000 feet while doing so. They wanted a range of thousands of miles without refueling, and they wanted its radar reflection to be as small as the laws of physics and the state of the art would permit. In 1958, there was nothing remotely like this in existence anywhere in the world. There were experimental rocket planes that had touched such speeds for a matter of seconds and then glided home with their paint scorched. There was no aircraft that could live there. You can hear the quiet desperation in a request like that. Nobody asks for the impossible casually. They ask for it when the alternative is blindness, and blindness in that decade meant guessing about the number of warheads pointed at your cities. Lockheed and Convair both submitted designs, refining them again and again across 2 years, and in the summer of 1959 the Lockheed proposal was selected. Johnson's team had worked through a long series of shapes designated with the letter A for Archangel, each one a little stranger than the last. The 12th of them was the one that flew, and this is the part worth holding on to as you drift towards sleep tonight, because it is the emotional foundation of everything that follows. Constraints are not the opposite of creativity. Constraints are very often the parent of it. A river given a wide, flat plain will wander lazily and go nowhere in particular, but force that same river through a narrow gorge, and it will cut stone. The engineers in Burbank were handed a gorge. They were told the aircraft must cruise where the air is thin enough to boil water at body temperature, at a speed where the air itself becomes a blowtorch, and they were told that ordinary aluminum, the metal every airliner in the world was built from, would soften and fail long before they got there. Every easy path was closed. Only the strange ones remained, and so they walked down the strange ones, one after another, and found something waiting at the end that nobody had ever built before. Kelly Johnson kept a set of rules taped where his engineers could see them, and the strange thing about those rules is how little they have to do with speed or altitude or physics. They are about people, a small team, a short chain of command, drawings released quickly, paperwork kept to the bare minimum that honesty demands. Fewer than 50 engineers on the core of the project, working in a building where the head of the program could walk from his desk to any drafting table in under a minute. Johnson believed, deeply and stubbornly, that complexity was a symptom of confusion. If a thing needed 12 parts, he wanted to know why it could not be done with 4. And that instinct, the reflex toward simplicity, is the reason the aircraft you are picturing right now looks the way it does. Because here is what most people assume when they first see the Blackbird. They assume that shape came from wanting to look futuristic. It did not. Every curve on that airplane is an answer to a question, and in most cases it is an answer to 3 or 4 questions at once. Johnson did not have the luxury of adding a component to solve each problem. At 3 times the speed of sound, every added surface is added drag, added heat, added weight, added failure. So the design had to fold its solutions into one another the way a well-made tool does until the shape stopped looking like an airplane and started looking like a conclusion. The work began in a wind tunnel and on a wooden pole in the desert, and those 2 places pulled in different directions. In the tunnel, the engineers were chasing airflow, watching how streams of smoke and pressure readings behaved over model after model at speeds no production aircraft had ever sustained. On the pole, out at a remote test site in Nevada, they were chasing something else entirely. There, a full-scale mock-up was hoisted into the air and bathed in radar energy while technicians measured what bounced back. Lockheed's radar specialists spent months learning a counterintuitive lesson. Flat surfaces and sharp right angles act like mirrors, throwing energy straight back to whoever sent it. Continuous curves, on the other hand, tend to smear a radar return outward in all directions, scattering it so thinly that the receiver hears only whisper. So the aerodynamists wanted one thing and the radar men wanted another, and the fascinating part is that they kept meeting in the middle at shapes nobody had ever drawn before. Johnson worked through a long sequence of configurations, each one labeled with a number after the letter A, and if you could lay them side by side, you would watch an ordinary-looking dart slowly grow stranger. Wings flatten and stretch, tails lean inward, and along the sides of the fuselage, something begins to emerge that had no real precedent in aviation. A pair of knife-edged shelves running forward from the wing roots all the way to the nose. Those are the chines, and they are the single most elegant thing on the entire aircraft. They began as a radar idea. A sharply tapered edge running the length of the forward fuselage helps deflect incoming energy away rather than reflecting it back, and it softens the blunt cylindrical shape that radar loves to find. That alone might have justified them. But when the models went into the tunnel, the engineers discovered something they had not fully expected. At high speeds and moderate angles of attack, those sharp edges shed powerful vortices, tight spinning ribbons of air that trail back over the fuselage and generate genuine lift. The body of the airplane was no longer just a container being carried by the wings. It had become part of the wing. Think about what that buys you. Lift from the fuselage means you need less wing area, and less wing area means less drag and less weight and less structure to keep cool. The vortices also improved stability and helped the aircraft behave predictably as it accelerated through the transonic region and beyond, where the center of lift wants to shift dramatically backward and pitch the nose down. The chines pushed lift forward, easing that shift, which reduced the amount of trim the pilot needed to hold. Less trim means less drag. Less drag means more range. More range means more of the Soviet Union photographed on a single tank of fuel, one shape. Radar, lift, stability, balance, range, all of it from a pair of edges that a passenger would glance at and call decoration. That is the philosophy in a single feature, and once you see it, you start seeing it everywhere on the aircraft. The two vertical tails cant inward toward each other rather than standing straight up, which reduces the flat surface a radar can catch from the side, and which also keeps them out of the worst of the hot exhaust flow. They were built with laminated composite structures rather than solid metal, chosen in part because those materials absorb radar energy instead of reflecting it. Wedge-shaped sections of that same absorbing material were tucked into the leading edges of the wings and along the chines, arranged so that the energy entering them was progressively soaked up rather than thrown back. Even the paint was part of the argument, loaded with tiny iron particles to help scatter and dissipate incoming radar. None of this existed in any handbook. There was no catalog to order from, no supplier to call, no accumulated body of practice to lean on. When your operating environment has never been visited before, neither have your solutions. The engineers found themselves inventing the vocabulary as they went, borrowing words from thermodynamics and chemistry and putting them into aeronautical drawings where they had never appeared. They had to define what a fastener meant when the metal around it would grow and shrink by inches with temperature. They had to describe fuel that would not be primarily fuel at all for much of the flight, but coolant. They had to talk about skin temperatures the way a foundry talks about a furnace. And the tools had to be invented too. The metal they eventually settled on, a titanium alloy chosen because it kept its strength at temperatures that would have left aluminum limp and useless, turned out to be almost hostile to conventional manufacturing. Standard cutting tools dulled almost immediately against it. Drills that would happily bore hundreds of holes in aluminum managed a handful in titanium before they were ruined. New bits had to be developed. New cutting speeds worked out by trial and error, new procedures written down for how to handle a metal that punished impatience. Even simple things betrayed them. Certain cleaning agents and even the trace chlorine in ordinary tap water could weaken the alloy over time, and cadmium-plated wrenches, the common tools of every workshop in America, left invisible deposits that would cause bolt heads to fail once the aircraft got hot. So they built a manufacturing culture from scratch, one that treated the metal less like a material and more like a temperamental collaborator. Look at the whole picture, and you begin to appreciate what a peculiar act of faith the design phase really was. Johnson and his team were drawing an aircraft with slide rules and pencils, calculating by hand the behavior of air at temperatures and pressures that had barely been measured, committing to a shape years before anyone could prove that shape would survive. They could not test their way to certainty. They could only reason carefully, simplify relentlessly, and trust the physics. There is a quiet lesson in that, and it is the one worth carrying with you as the room gets darker and your breathing slows. The Blackbird looks the way it looks because almost every comfortable option was taken away. Aluminum was forbidden by heat, bulk was forbidden by drag, extra systems were forbidden by weight. Sharp corners were forbidden by radar, and when you strip away every path that is merely convenient, what remains is not compromise. What remains is the shape the problem always had, waiting to be uncovered. The most beautiful objects human beings have made were rarely made by people with unlimited freedom. They were made by people boxed in on every side who kept asking what else the box would allow. A team of engineers in California, given a set of demands that bordered on fantasy, kept asking that question until the answers merged into one long black silhouette. It had never existed before, and soon, in the dry heat of a Nevada lake bed, it would need to prove it could fly. Touch the skin of a blackbird after it lands and you will pull your hand back. Not because the metal is cold, though the aircraft has just come down from air that hovers near 60 degrees below zero. You pull your hand back because the airframe is still hot enough to cook on, an hour after the flight, radiating warmth into the desert evening like a stone pulled from a fire pit. Ground crews learned to wait. They learned to let it cool on its own terms, the way you let a cast iron pan sit on the stove. And that single detail, more than any statistic about speed, tells you what kind of machine you are looking at. The heat came from nothing more exotic than air. At 3 times the speed of sound, the atmosphere no longer flows politely around a wing. It gets compressed, squeezed, and rubbed against every surface until friction and pressure turn motion into temperature. On a normal cruise, the Blackbird's skin sat somewhere between 500 and 600 degrees Fahrenheit across most of the fuselage. Near the nose and the leading edges of the wings, in the places where the air hit first and hardest, it climbed past 900. Certain spots near the engine nacelles reached higher still. That is not a warm airplane. That is a slow bake sustained for hours over the entire outer shell of the machine. Aluminum, the material that had built essentially every serious aircraft of the previous quarter century, simply cannot live there. It softens, it sags, it loses the very stiffness that lets a wing hold its shape against the weight of the air beneath it. Steel could take the heat, but steel is heavy, and weight is the tax you pay on every mile of range and every foot of altitude. So the engineers went looking for something else, and they found a metal that most of American industry at the time regarded as strange, expensive, and a little bit theoretical. Titanium is the 9th most abundant element in the Earth's crust, which sounds like a comfort until you learn how difficult it is to get it out of the ground and into a usable sheet. It binds tightly to oxygen, It has to be coaxed through a chemical process before it becomes metal at all. But when you finally have it, what you hold is remarkable, roughly as strong as many steels, yet nearly half the weight. And crucially, it holds onto that strength at temperatures that would leave aluminum limp. For an aircraft that would spend hours inside its own private furnace, there was really no alternative. Around 90% of the Blackbird would eventually be built from titanium alloy. Here is the part of the story that always makes people smile in the dark. In the early 60s, the largest and most reliable supply of high-grade titanium ore in the world lay inside the Soviet Union, the very country the aircraft was being built to photograph. So the CIA quietly arranged purchases through a web of front companies and third-party dealers scattered across the globe, buying ore from bogus firms with unremarkable names, never once revealing what it was for. Soviet titanium, sold at a profit, flowed westward and became the skin of the airplane that would fly over Soviet territory faster than anything the Soviets could launch at it. History rarely offers irony that clean. Getting the metal was only the beginning of the trouble. Titanium turned out to be almost personally offended by ordinary factory practice. Standard cutting tools went dull in minutes. Drill bits that would punch hundreds of clean holes through aluminum managed perhaps 17 holes in titanium before they were scrap. So Lockheed's engineers developed their own bits, worked out their own cutting speeds by patient trial and error, and wrote entirely new procedures for a metal that punished anyone in a hurry. Welding it required flooding the joint with inert gas, because hot titanium will greedily absorb oxygen and nitrogen from the surrounding air and turn brittle as glass. Some assemblies had to be welded inside sealed chambers filled with argon, workers reaching in through gloved ports like surgeons at an operating table. And then came the small betrayals, the ones nobody could have predicted. Spot-welded panels made during the summer months kept failing, while identical panels made in winter held perfectly. The mystery took weeks to solve. The city of Burbank chlorinated its water more heavily in summer to control algae, and that extra chlorine present in the water used to wash the parts was quietly attacking the alloy. From then on, the panels were rinsed in distilled water only. Cadmium-plated wrenches, the ordinary tools hanging in every workshop in America, left microscopic traces of cadmium on bolt heads, and once the aircraft got hot, those traces caused the bolts to fail outright. Every cadmium tool had to be hunted down and removed from the plant. Even ordinary marker pens were banned because the ink could eat into the metal. So they built a new manufacturing culture, part chemistry lab, part temple. Each batch of titanium was sampled and tested before use. Roughly 1 batch in 10 was rejected outright and sent back. They learned to pickle the metal in acid baths to strip away contamination. They learned which lubricants were safe and which were quietly corrosive. They were not simply building an airplane. They were teaching an entire industry how to handle an unfamiliar element, one hard-won lesson at a time, and writing the manual as they went. Even with the metal mastered, one enormous problem remained, and it is the one that produces the Blackbird's most famous quirk. Heat makes things grow. Over the course of a high-speed cruise, the airframe expanded so much that the aircraft became measurably longer by several inches from nose to tail. If you build a rigid structure and then heat it unevenly by hundreds of degrees, it does not gracefully stretch. It buckles, warps, and tears itself apart at the seams. So the engineers stopped fighting the expansion and started designing for it. The wing skins were given shallow corrugations, gentle vertical ripples running along the surface, so the panels could open and close like the folds of an accordion as they heated and cooled. Kelly Johnson took some teasing for that. since corrugated skin evoked the tin-roofed biplanes of a much earlier era. He simply pointed out that it worked. The fuel tanks got the same treatment in reverse. On the ground, cold and unstretched, the panels of the fuselage did not quite meet. The joints were deliberately loose, and so the aircraft sat on the tarmac dribbling fuel onto the concrete, forming slow puddles beneath it, looking for all the world like something broken. It was not broken. It was simply waiting, only in flight, only when the friction heat arrived and the metal swelled outward and every panel pressed tight against its neighbor, did those seams finally close and the tanks become sealed. The Blackbird was an aircraft that only became watertight at speed. Which brings us to the image worth carrying into sleep tonight. Think of a snake, dull and stiff, its skin clouded and ill-fitting, moving awkwardly through the grass. Then think of it shedding, emerging bright and taut and perfectly fitted to itself. The Blackbird did something like that on every single mission. On the ground it was loose in its own skin, leaking, sagging slightly, uncomfortable in the world of ordinary temperatures. It only became truly itself once the air had wrapped around it and heated it and drawn it out to full size. The shape you saw on the runway was not the real shape. The real shape existed only at 80,000 feet. And here is the contradiction that gives the machine its strange poetry. Nearly every aircraft ever designed treats heat as an enemy, something to be shed, insulated against, vented away. The Blackbird welcomed it. Its fuel was pumped through the leading edges and the engine parts as coolant before it was ever burned, using the heat to warm itself toward ignition. Its black paint, the very thing that gave it its name, was chosen partly because dark surfaces radiate heat away more efficiently than bright ones, and partly because the iron particles suspended in it absorbed radar energy. The color was cooling and camouflage at once, a machine that grows to fit itself, a skin that seals only when it burns. Somewhere out there in the dark, in a museum hangar with the lights turned low, one of them is sitting perfectly still, several inches shorter than it once was in flight, waiting for an air it will never taste again. Hang two of them under a pair of enormous nacelles, one on each wing, and you have the loudest, hottest, strangest pair of lungs ever bolted to an airplane. The Pratt & Whitney J58 was not really one engine. It was two ideas living inside the same casing, taking turns depending on how fast the world was rushing past. Here is the simple picture first, and it is worth settling into slowly. A normal jet engine works by grabbing air, squeezing it, setting it on fire, and shoving it out the back. The squeezing is done by a compressor, a stack of spinning blades driven by a turbine further down the pipe. It is elegant, and it is reliable, and it works beautifully from a standstill up to somewhere around twice the speed of sound. Beyond that, the whole arrangement begins to suffer. The air arriving at the front is already so violently compressed by the aircraft's own motion, and already so hot from that compression, that the spinning machinery in the middle stops being a help and starts being an obstacle. Blades have limits. Metal has limits. Push a conventional turbojet to Mach 3 and you are asking the compressor to do work that the sky is already doing for free, while the turbine behind it slowly cooks. There is another kind of engine that solves this, and it has almost no moving parts at all. A ramjet is essentially a carefully shaped tube. Air enters the front at tremendous speed, the geometry of the tube slows and compresses it, fuel is added, the mixture burns, and the exhaust leaves faster than the air arrived. No compressor, no turbine, just shape and speed and flame. The problem with a ramjet is that it needs to already be moving quickly to work at all. Sitting on a runway, it does nothing whatsoever. It is an engine that cannot start itself, so the engineers did something that sounds obvious once you hear it and was fiendishly difficult in practice. They built an engine that begins its life as a turbojet and gradually becomes something very close to a ramjet as the aircraft accelerates, without ever shutting down or changing over in one abrupt moment. The transition happens by degrees, like a tide coming in. The mechanism was a set of 6 large tubes running along the outside of the engine, from a point about a third of the way through the compressor all the way back to the afterburner. As the Blackbird pushed past roughly Mach 2, valves opened and a growing share of the incoming air was simply allowed to bypass the hot core entirely. Instead of being crammed through the remaining compressor stages and the burner and the turbine, that air slid down those 6 pipes and arrived directly at the afterburner where fuel was waiting for it. The core kept turning, kept doing useful work, kept driving the fuel pumps and the accessories, but more and more of the actual thrust was being produced further back in a chamber that was functionally a ramjet with a turbojet hanging off the front of it. Picture it as breathing in rhythm with the sky. At low speed, the engine inhales in short, mechanical gulps, the compressor doing all the grasping. As the aircraft accelerates, the breath lengthens and smooths out, the sky itself beginning to push air down the throat, until at cruise the machine is barely working to inhale at all. It simply opens its mouth and lets 80,000 feet of thin, screaming air pour in. Something like 8/10 of the thrust at full cruise came not from the engine's spinning heart, but from the shape of the inlet ahead of it and the nozzle behind it. The engine had become a partner to the airframe rather than a passenger inside it. That inlet deserves its own quiet moment of admiration. At the front of each nacelle sat a movable cone, a spike, pointed forward like a needle. As speed increased, that spike translated backward, sliding as much as 26 inches into the nacelle, adjusting the geometry of the shock waves so that the strongest one sat exactly where it was needed, just inside the lip. Get it right, and the inlet delivered air to the engine at a fraction of the speed it had arrived at, compressed by a factor of 40, all for free, all through geometry. Get it wrong, and the shock wave popped out the front in an event pilots called an unstart, a sudden violent yaw as one engine lost its air and the other kept pushing. Later automatic systems learned to catch these within fractions of a second, and the ride grew calmer as the years went by. Now the fuel, because this is where the story turns almost gentle. You cannot put ordinary jet fuel into an aircraft whose tanks reach temperatures that would boil water many times over. Ordinary fuel would vaporize, pressurize, and become a very serious problem. So Shell and the Air Force developed a fuel that essentially refuses to burn under normal conditions. JP7 had a flash point around 60 degrees Celsius, roughly 140 Fahrenheit, which means you could drop a lit match into a puddle of it and the match would simply go out. Cruise demonstrated exactly that, to the polite alarm of onlookers. Cigarettes were extinguished in it. It sat there stable and unbothered, waiting. That stubbornness was the whole point, because the fuel had a job to do before it ever reached the burner. JP7 circulated through the airframe as coolant, drawing heat out of the cockpit air conditioning, the hydraulic systems, the engine oil and the leading edges, arriving at the fuel nozzles already hot, already primed, carrying with it the very energy that friction had put into the aircraft. It also served as hydraulic fluid for the afterburner nozzle actuators. Nothing was wasted. The heat that would have destroyed the airplane was collected, carried inward and burned. But if the fuel will not light, how do you light it? With a small chemical trick. A separate tank held triethylborane, a compound that ignites spontaneously the instant it meets air. No spark required. A measured shot was injected into the combustor to start the engine, and another shot each time the afterburners were lit, with only 16 shots available per engine per flight. The visible signature was a brief flare of green in the exhaust, a soft emerald flash in the moment before the orange came. Ground crews watching a night departure saw those green pulses first, one per engine, then the long twin torches unrolling behind the aircraft. Asked the men who flew it what full power felt like, and the answers tend toward the physical rather than the technical. Standing at the end of the runway with the brakes held, the noise was less a sound than a pressure on the chest, a low battering that you felt in the sternum and the teeth. Then the afterburners lit and something shoved, not a smooth swell, but a distinct kick in the back, twice, one for each engine, and the runway markers began arriving faster than the eye wanted to track them. Higher up, in the acceleration through the transonic region and out the far side, the sensation changed character entirely. It became patient. The airplane simply kept going, kept climbing, kept adding speed in a long, unhurried curve, and the noise fell away behind because the aircraft was outrunning it. At cruise, the cockpit was quieter than a subsonic airliner. All that fury was happening astern, unheard. That is the thing worth carrying with you tonight. 2 engines, each producing something over 32,000 pounds of thrust, burning a fuel that would not catch fire from a match, lit by a chemical that catches fire from nothing but air, breathing through inlets that rearranged invisible shock waves 26 inches at a time. Every one of those elements is on its own a description of something dangerous. Put together correctly with enough understanding, they produced one of the smoothest rides in aviation history. There is a kind of peace in that. Fire is only frightening when it is loose. Contained, understood, given exactly the right amount of air and exactly the right moment to begin, it becomes the steadiest thing in the sky. The J-58 did not tame speed by fighting it. It listened to the oncoming air, adjusted its breathing, and let the sky do most of the work. Somewhere above the weather, for hours at a time, that arrangement held, and it held every single time. At 80,000 feet, the sky stops being blue. It happens gradually over the course of a long climb, and the crews who flew the Blackbird describe it almost as a slow dimming of the lights. First, the horizon flattens, then it curves gently the way the edge of a very large plate curves when you look along it. Above you, the color drains out of the atmosphere and turns a deep indigo, then something closer to black. And if you shade your eyes from the glare of the instrument panel, you can pick out stars at 2 in the afternoon. Below you there is weather, all of it, every thunderstorm and every airliner and every cloud deck in the world, compressed into a thin white rumpled layer that no longer has anything to do with you. Roughly 99% of the atmosphere is beneath your wings. What remains is a bright band along the curve of the Earth, only a few miles thick, glowing pale blue at its base, and fading to nothing above. That band is the entire breathable envelope of the planet, and from up there it looks impossibly thin. The Blackbird did not fly in space, but it flew close enough to borrow the view. Getting a human being to that altitude alive required something closer to spaceflight than to aviation. Above about 63,000 feet, at what physiologists call the Armstrong limit, the air pressure drops so low that water boils at the temperature of the human body. Not warm water, body temperature water. The saliva on your tongue, the moisture in your lungs, the fluid in your tissues, nothing short of a sealed, pressurized garment can keep a person conscious and intact in that environment for more than a handful of seconds. So the crews did not wear flight suits in any ordinary sense. They wore full-pressure suits built by the David Clark Company, the same firm whose work threaded through the Gemini and Apollo programs, and the resemblance was not a coincidence. Gold-plated visor, locking gloves, layered restraint fabric over an airtight bladder, a helmet that sealed at the neck ring with a solid click, after which the outside world could only reach you through a microphone. The ritual before each flight was slow and deliberate, and there is something almost monastic about it. A physical examination, a high-protein, low-residue meal, most famously steak and eggs, chosen because it left as little as possible in the digestive system for the next several hours. Then a period of breathing pure oxygen, sometimes an hour or more, to purge dissolved nitrogen from the bloodstream and prevent the bends, exactly as a diver decompresses in reverse. Technicians helped each man into the suit, checked every seal, inflated it to test for leaks, and then walked him to the aircraft carrying a portable cooling and oxygen unit like a small suitcase. He could not put on his own gloves. He could not scratch his own face. For the next 4 or 5 hours, sometimes longer, he would be sealed inside a personal atmosphere, drinking through a tube fed into a port beneath the visor, eating soft food from a squeeze container if he ate at all, and the airplane around him was hot. That is the detail that surprises people. Outside, the air at 80,000 feet is around 60 degrees below zero, but friction heated the windscreen to something near 300 degrees Fahrenheit, hot enough that crews were warned not to press a gloved hand against the glass for long, hot enough that men warmed their lunch by holding it up against the quartz. The cockpit air conditioning worked constantly, dumping heat into the fuel, and still the suit's own cooling loop was the only thing that made the cabin bearable. Ejection at that altitude and that speed was survivable, and it had been done, but it was not something anyone dwelt on. The suit was the last line. Everything else was courtesy. Now consider the problem of knowing where you are. At 32 miles per minute, a navigational error is not a small inconvenience. Drift a few degrees for 90 seconds and you have missed the target entirely, or worse, crossed a border you were never meant to touch. Satellite navigation did not exist in usable form when the Blackbird entered service. Radio beacons were useless in the places it worked, so Lockheed and Nortronics reached backward, past every modern method, all the way to the oldest technique human beings ever devised for finding themselves on a featureless surface. They gave the aircraft the stars. Behind the cockpit, set into the upper fuselage, sat a small circular window. Beneath it lived an astro-inertial navigation system, a device the crews nicknamed R2-D2 long before anyone had a better reason to. Inside was a telescope on a gimbal and a catalog of star positions, 52 of them in the earliest versions, 61 in later ones, along with the mathematics to know where each should appear at any moment of any day of any year. Using a blue light filter that cut through the scattered daylight, the tracker could find and lock onto those stars in broad afternoon sun, because at 80,000 feet there is little enough air left overhead that the stars never truly go out. Every few seconds it took a fix, compared the answer to what the inertial platform believed, and quietly corrected the difference. The result was a machine that could place itself within a few hundred feet after hours of flight across an ocean, guided by the same points of light that Polynesian navigators and Portuguese captains once steered by. There is something wonderfully human about that. The most advanced aircraft on Earth, built of titanium and shock waves, finding its way home the way sailors did 3,000 years ago. The records came when they came, almost as an afterthought. On the 28th of July 1976, flying out of Beale Air Force Base in California, Captain Eldon Jowers and Major George Morgan pushed an SR-71 through a measured course at 2,193 miles per hour. The same day, Captain Robert Helt and Major Larry Elliott held a Blackbird in sustained horizontal flight at 85,069 feet. Both figures still stand for air-breathing aircraft. Nobody has taken them back. 2 years earlier, on the 1st of September 1974, Major James Sullivan and Major Noel Whitfield flew from New York to London in 1 hour 54 minutes and 56 seconds, which meant they landed by the clock on the wall at a time that felt like it belonged to the flight before theirs. 12 days after that, another crew ran London to Los Angeles in 3 hours and 47 minutes, chasing the sun westward and very nearly keeping up with it. But the numbers are the least interesting part. Ask the men what it actually felt like, and they rarely start with speed. They start with silence. At cruise, the Blackbird was smooth, quieter than a commercial cabin, the engines a distant presence rather than a roar. The stick moved in small increments. The airplane did not feel fast, it felt suspended. The sensation of velocity came only from watching the ground where an entire state slid beneath the nose in the time it takes to drink a cup of coffee, where a river you noted a moment ago was already 90 miles behind. Turning that aircraft took a radius measured in 100 miles or more, which meant a course change over Europe might begin over one country and finish over another. Crews spoke of watching the Terminator, the line between day and night, and realizing they were gaining on it, and the machine was working the whole time. Its cameras and radar could survey something on the order of 100,000 square miles of the Earth's surface in a single hour, mapping in 60 minutes an area larger than most nations, all of it stitched to precise coordinates by that patient little telescope reading the stars overhead. So picture it once more before you drift off. A dark violet sky, a curved white earth, a man sealed in a golden helmet, breathing bottled air, sipping water through a straw, sitting almost perfectly still while the planet unspools beneath him at a mile every second and a half. No noise, no sense of hurry, just the soft hiss of the suit, the glow of the instruments, and the oldest navigational partners humanity ever had, quietly holding the aircraft on course from 93 million miles away and further. The men who flew the Blackbird did not look like the pilots in the recruiting posters. They were, for the most part, older than you might expect, in their 30s and early 40s, often married with children, often carrying more than 1,500 hours in fighters before anyone at Beale would even return their phone call. That was deliberate. The Air Force was not looking for daring, it was looking for steadiness. The selection process took days and felt less like a flight evaluation than a long, patient conversation. Candidates were flown to Beale Air Force Base in Northern California, given a physical on the order of what astronauts endured, and then interviewed at length, not only about flying, but about their lives, their marriages, their tempers, their habits. Wives were interviewed too. The program wanted to know whether a man could disappear to Okinawa or England for weeks at a time without anything unraveling behind him. Of those who applied, only a small fraction were ever offered a seat, and the ones chosen were rarely the loudest voices in the room. They came in pairs. Every Blackbird carried 2 men, a pilot in the front seat, and a reconnaissance systems officer, the RSO, in the back. And once a pair was matched, they generally stayed matched, sometimes for years. That was unusual in military aviation, where crews are typically shuffled like cards. But the Blackbird demanded something closer to a marriage. The pilot flew the aircraft and managed the inlets, the fuel, the engines, The RSO ran the navigation, the sensors, the defensive systems, and the mission timing, calling headings and turn points that had to be hit within seconds. At a mile every second and a half, there was no time to explain yourself. You learned the rhythm of the other man's voice, the way he breathed when something was wrong, the half-second pause that meant he was already fixing it. Crews described finishing each other's checklist items without looking, communicating in fragments that would have been unintelligible to anyone else in the squadron. Training began in the simulator, which many crews found harder than the airplane itself, because instructors could stack failures on top of one another in ways the real aircraft rarely bothered to. Then came the SR-71B, the two-seat trainer with its instructor cockpit raised up behind the students, a strange humped silhouette that let the man in back actually see the runway during landing. Only two of those trainers were ever built. Every Blackbird pilot in history passed through them. And then there was the ritual before each flight, which is where the whole thing starts to feel less like military aviation and something more like preparation for a dive into deep water. Mission planning began days ahead, the route drawn to the minute, tanker rendezvous points fixed over oceans, fuel loads calculated for every leg. The morning of the flight, the crew reported for a high-protein, low-residue meal, the famous steak and eggs, chosen because it would sit quietly in the body for hours inside a sealed suit. Then a physical exam. Temperature, blood pressure, a look at the ears and throat, because a head cold at 80,000 feet was not an inconvenience, it was a disqualification. Then the suit-up room where two technicians from the Physiological Support Division, the same specialists who dressed astronauts, assembled the crew piece by piece into their pressure garments, undergarments, then the suit, then the gloves locked to the wrists, then the helmet locked to the neck ring. From that moment, the man was breathing bottled oxygen, and he would keep breathing it for the next half hour or more, sitting in a reclined chair with a portable oxygen unit in his lap, saying almost nothing. This was the nitrogen purge, flushing dissolved gas out of the bloodstream so it could not bubble at altitude. But listen to how crews described that half hour, and it stopped sounding medical. They called it quiet time. They sat there in the cool room with the hiss of oxygen filling their helmets and mentally flew the entire mission from engine start to landing. Every turn, every refueling, every failure they might meet and what their hands would do about it. Slow breathing, eyes closed or half closed, no conversation. It was, in every practical sense, a meditation, and the men who did it well arrived at the aircraft already halfway through the flight. They were driven to the jet in an air-conditioned van, still tethered to their portable oxygen, and lifted into the cockpit by the same technicians who strapped them in, connected the suit hoses to the aircraft systems, and checked every fitting twice. Below them, the crew chief and the ground team were finishing their own long list, and somewhere in that handover, between the men on the ladder and the men in the seats, was the whole architecture of trust the program was built on. It had to be, because things went wrong. In the earlier years, before the digital control system arrived in the 1980s, the inlets could unstart, meaning the shock wave standing inside that carefully tuned intake would suddenly spit forward and out, and the thrust on one side of the aircraft would collapse in an instant. The airplane would slew violently, hard enough to slam a helmeted head against the canopy rail, hard enough to leave bruises. Crews learned to expect it, to recognize it by feel before the instruments confirmed it, and to work the restart sequence with their hands while their bodies were still being thrown around. Generators failed, fuel lines developed leaks, cockpit air conditioning quit, and the temperature climbed while the friction outside kept doing what friction does. In nearly every account you read of these moments, the striking thing is the absence of drama in the telling. Nobody shouts. Somebody says the inlet's gone. Somebody else says restarting. And the sentence after that is usually about the next turn point. The hardest test of all came on the 25th of January, 1966, over northeastern New Mexico. Bill Weaver was flying with Jim Zwayer, a Lockheed Flight Test Reconnaissance Systems officer, at Mach 3.18 and around 78,000 feet, when an inlet unstarted during a turn and the aircraft departed controlled flight. The forces that followed tore the Blackbird apart around them. Weaver later said he was certain he had died. He never pulled the ejection handle. He was thrown clear of the disintegrating airframe, his pressure suit inflating automatically and holding him together in air far too thin to breathe, his faceplate frozen over so completely that he woke under an open parachute, unable to see anything at all. Zwayer did not survive. Weaver came down in ranch country, was found by a rancher who happened to have a helicopter, and was flying again within 2 weeks. The suit worked, the training worked, the parachute deployed on its own, exactly as designed. The disaster was survived not by heroics but by preparation laid down years earlier by people who had imagined this exact moment and quietly built for it. Ask a Blackbird crewman about the aircraft and something interesting happens in the language. They almost never call it equipment. They call it she. They talk about the airplane letting them know things, about the way a particular jet handled differently from its sisters, about how you had to fly the machine the way it wanted to be flown rather than the way you preferred. Each airframe had a personality shaped by tiny variations in how it was hand-built and hand-repaired. Crews knew which ones ran cool, which ones drank fuel, which ones needed a little extra coaxing through the transonic region. They spoke of the moment past Mach 2.6 when the aircraft seemed to settle and smooth out, and they described it not as the machine performing, but as the machine finally arriving where it wanted to be. That is the quiet lesson underneath all of it. The most extreme flying machine ever put into regular service was not conquered. It was accompanied. The men who flew it did not overpower the danger. They studied it until it became familiar, then dressed carefully, breathed slowly, and went to meet it. The whole enterprise, from the argon welding chambers to the star tracker to the half hour of silent oxygen in a reclining chair, was an act of preparation so thorough that the extraordinary became routine, and routine, in the end, is a peaceful thing. 2 men in golden helmets, sealed and calm, sitting in a machine they knew the way you know an old friend's handwriting, sliding across the top of the world without hurry, without noise, and without fear. Nothing dramatic ended the Blackbird. There was no final mission gone wrong, no shoot-down, no failure of the machine itself. What ended it was arithmetic and the slow turning of the world it had been built to watch. By the late 1980s, the SR-71 program was costing somewhere between $200 and $300 million a year, and it needed an entire private empire to stay airborne. Its own tanker fleet of KC-135Q aircraft, carrying JP-7 that no other aircraft in the inventory could burn. Its own spare parts, machined from titanium by tooling that no longer existed anywhere else. Its own physiological support teams, its own suit technicians, its own detachments scattered from Kadena in Okinawa to Mildenhall in England. Every hour in the air demanded many hours on the ground, and the men who signed the checks began asking a question that has ended more aircraft than any missile ever has. Do we still need this, and can something cheaper do it instead? The honest answer in the world of 1989 was complicated. The Berlin Wall came down in November of that year, and though nobody could yet see how quickly the Soviet Union itself would unravel, the sense of an era loosening its grip was already in the air. The Blackbird had been conceived as an answer to a very specific fear, the fear of not knowing what was being built behind a closed border. And by the end of the 80s, the not knowing had a different solution. Satellites had grown up. That transition deserves a moment because it was not sudden. When the first Blackbirds flew, reconnaissance satellites dropped their exposed film back through the atmosphere in capsules that had to be snatched out of the sky by aircraft trailing hooks, and if the weather was bad or the timing was off, the pictures could be lost in the ocean. But in December of 1976, a satellite went up carrying a digital imaging system that needed no film at all. It could see and it could send what it saw home in something close to real time relayed down through other satellites to analysts sitting at screens. Over the following decade, that capability multiplied and matured. The sky filled quietly with eyes that never needed a pressure suit, never needed a tanker, never needed a runway long enough to accelerate 140,000 pounds of titanium into the air. The Blackbird's defenders made the counter-argument, and it was a good one. A satellite's orbit is a known thing. Any nation with a pencil and a clock can work out when the eye passes overhead and simply roll the tarpaulins over whatever it prefers not to be seen. An SR-71 could appear when nobody had planned for it, cross a target at 33 miles a minute, and be gone before the decision to hide anything could travel down a chain of command. The airplane offered surprise, and surprise is a kind of information all by itself. But budgets rarely turn on elegance of argument, and in 1989 the decision came down. The Air Force would retire the SR-71 the following year, so the last flights were flown, and they were not sad occasions so much as ceremonial ones. There were farewell sorties from Beale Air Force Base in California, and crews landed to find fire trucks arching water over the taxiway and families waiting on the ramp. And then, on the 6th of March 1990, came the flight that everyone remembers. Aircraft number 972 was to be delivered to the Smithsonian, and the Air Force decided that if it was going to fly across the country one last time, it might as well do so with the throttles where they belonged. Ed Yielding and Joseph Vida took off from California and headed east. In 1 hour, 4 minutes, and 20 seconds, they were over Washington, D.C. coast to coast, ocean to ocean. They covered 2,124 miles in 67 minutes and 54 seconds, averaging better than 2,100 miles an hour. Along the way, they set records nobody had thought to formalize before, including a leg from St. Louis to Cincinnati that took 8 minutes and 32 seconds. Then they slowed, descended, and made a series of passes over Dulles International Airport, wheels down, engines throttled back, the great dark shape sliding low over a crowd that had come to watch a thing end. And when they landed and shut down, the ground crew chalked the wheels. The crew climbed out in their orange suits, and the aircraft that had just crossed a continent in the time it takes to eat lunch was towed away to be a museum piece. It was not quite the end, and that is part of the gentleness of this story. Congress, uneasy about the gap the retirement had opened, voted money in 1994 to bring 3 aircraft back, and for a couple of years in the mid-90s, Blackbirds flew again out of Palmdale, tested and certified and ready for a call that never quite came. The funding was struck down, restored, struck down again in the political back and forth of the late 90s, and the airplanes drifted into storage. NASA kept 2 of them flying a while longer at what is now Armstrong Flight Research Center, using them as high-altitude laboratories, letting scientists ride the edge of the atmosphere for sonic boom studies and aerothermal research. The final flight of an SR-71 anywhere in the world took place on the 9th of October, 1999, at an air show. It flew, it landed, and that was that. No missiles, no drama, no loss. Just a long exhale after 37 years. 32 SR-71s were built. 12 were lost over the decades to accidents, mechanical failures, and the sheer difficulty of the flight regime. Not one was ever lost to an enemy. Somewhere north of 1,000 surface-to-air missiles were fired at Blackbirds over the course of the program, and every single one of them arrived where the aircraft used to be. And here is the part that still catches people off guard all these years later. The records have not fallen. On the 28th of July 1976, Eldon Jors and George Morgan flew a straight course at 2,193 miles an hour, and on that same day Robert Helt and Larry Elliott held level flight at 85,069 feet. Both marks stand today as the absolute records for a jet-powered aircraft in level flight. The New York to London run of 1 hour, 54 minutes and 56 seconds, set in September of 1974, has never been challenged by any air-breathing aircraft. Rockets have gone faster, rocket planes have gone higher, but nothing that takes off from a runway, cruises for hours, and lands on a runway has ever matched what a machine designed with slide rules and drafting tables did before most people listening tonight were born. There have been proposals since: hypersonic demonstrators, unmanned concepts, aircraft sketched on the promise of engines that breathe air at 5 times the speed of sound. Some of them may yet fly, but no successor has been built and flown and put to work, and so the Blackbird's place in the record books has simply been left alone, the way a mountain is left alone. The reason is not that we forgot how. It is that the world stopped needing exactly that answer to exactly that question, and the extraordinary things we build are always answers to questions somebody was once desperate to solve. Which brings us back to where we started, on a warm concrete ramp with fuel dripping quietly from the seams of an airplane that has not moved. That puddle was never a fault. It was the price of a machine designed to be whole only when it was hot, only at 80,000 feet, only when it was doing the one thing it was born to do. On the ground it was always slightly wrong, always slightly uncomfortable, always waiting. The Blackbirds are on the ground now, all of them, in museums from Virginia to Seattle to the Californian desert where they were born. They do not leak anymore because they never get warm. Children walk beneath those long black chines and reach up toward wings that once flexed and rippled with heat, and the metal is cool to the touch and perfectly still. It is a good ending, really. A machine built out of fear and brilliance and a great deal of patience, flown by careful people in golden helmets who never lost one of their own to an enemy, now resting under museum lights with nothing left to prove. The engines are silent, the star tracker is closed, and the sky it once owned goes on turning above it, quiet, dark, and endlessly deep.